Greetings students, and welcome back to another lesson on complex variables. In this video I'm going to define branch points and branch cuts and build a foundation that will allow us to perform complex integration of functions with branches. To build this foundation, I'll start by discussing the natural log of a complex number z. Suppose I have a function w equals f of z, which equals ln of z. If you remember my very first video on complex variables, you'll recall that I can write any complex number as its real part plus I times its imaginary part. In the case of w, I can write it as u plus iv, where u and v are real numbers. I can also write a complex number z in the complex plane as a polar representation, with z being the distance from the origin r times the exponential of I times the angle relative to the positive real axis theta. In that case, the natural log of z will become the natural log of r plus I times theta. Note that r and theta are both positive real numbers. If I now rearrange this equation and take the exponential of both sides, here's what I'll get. And since w is just u plus iv, I can rewrite the left-hand side to get the exponential of u times the exponential of iv. If we now equate the real and imaginary parts of both sides, we find that the exponential of u must equal r, and that the exponential of iv must equal the exponential of I theta. Solving the u equation is pretty easy. U is just ln r. But to solve the v equation, we have to expand out with Euler's formula. If we do that, here's what we'll get on both sides. Now, if we equate the real and imaginary parts in this v equation, we'll get two equations involving sine and cosine. Now, if cosine and sine v are respectively equal to cosine and sine theta, that must mean that v is just theta plus 2 pi n, where n is some integer. The reason for this is that if I take theta and add any multiple of 2 pi, I get the same value for sine and cosine that I had with theta originally. Remember, sine and cosine have a period of 2 pi. So that's why, in general, v must equal theta plus 2 pi n to account for that general 2 pi periodicity. Finally, since w is u plus iv, w is just ln r plus I times theta plus 2 pi n if we plug in the u and v. And this right-hand side is equivalent to ln z then, since w is just ln z. Now, r is just the magnitude or modulus of z. It's the distance of z from the origin. So in terms of z, the natural log of z is given by the following equation, where n once again is an integer. Let's take a natural log of some random complex number to illustrate this expression. If I had this number a on the complex plane, which was a distance given by the magnitude of a from the origin, and an angle of theta a relative to the positive real axis, its natural logarithm would be given by ln a plus I times theta a plus 2 pi n, where n is once again an integer. Here's the strange thing about ln a. The natural log of the magnitude of a is a unique number, but the imaginary part is not a unique number. I can have any integer value of n that I want, and it would still be an equally valid answer for the natural log of some complex number a. Ln a, as a result, has multiple answers corresponding to different values of n. It doesn't just have a single unique value we're used to seeing with most functions. It's what we call a multiple valued function. So in general, ln z is a multiple valued function because of this n. Technically, that goes against the definition of function, but whatever, complex variables often throw a wrench into typical intuition. Now, this multiple valued function is a contrast with typical single valued complex functions. Something like z squared, which would be r squared times the square of this trigonometric term, would only be a single valued function. Why is that? Because it doesn't matter what angle I substitute, whether it's theta, theta plus 2 pi, theta plus 4 pi, etc., I will still get a unique value for z squared given a single value of z. The sine and cosine in here eliminate the multiple of 2 pi difference and make these different arguments, theta, theta plus 2 pi, etc., they make these different arguments redundant. The natural logarithm, however, by virtue of its nature, extracts the redundancy hidden by the sine and cosine and lays it out for the world to see. This 2 pi n is no longer masked by a sine and cosine. It's now an essential feature that makes the natural log a multiple valued function. Normally, though, the sine and cosine would mask the 2 pi n because they are 2 pi periodic, but not in the case of the natural logarithm. Hopefully, this explanation should drill home why the natural log is a multiple valued function. By extension, any complex function that is expressed in terms of the natural log is therefore usually multiple valued. Okay, let's move on to the next concept which arise as a result of multiple valued functions, the ideas of branch points and branch cuts. Let's say z is a complex number defined by this polar representation. As we've discussed, the natural log of z is given by this equation. I can change this imaginary term to another angle, capital theta, and end up with the following. The problem with this natural log is that it's multiple valued, as I mentioned above. However, it is possible to convert this multiple valued function to a single valued function. To do that, we can just restrict the capital theta to lie between some arbitrary real argument alpha and then alpha plus 2 pi. In performing this restriction, what we've done is we've created a branch of the natural log function. A branch of a multi-valued function f is a single-valued function g. This g must be analytic in a domain, and for each complex number z in this domain, g of z would take on one of the values of f. Remember, g of z must be analytic to be a branch of f. If it's not analytic, then g of z could just take on a bunch of random values of f, and that's not quite a branch. That's why g must be analytic. Anyway, the branch of our natural log function is given by this function g of z, where capital theta is now restricted into this 2 pi interval. Now if I draw the complex plane, then the branch I've defined using this alpha to set up an interval of length 2 pi is created using the straight line of arc z equals alpha. This straight line that I use to create the branch is called the branch cut. It's a portion of a line or curve used to create a boundary that makes a multiple valued function into a single valued function. In this case, the imaginary part of our ln function can go from alpha to alpha plus 2 pi, not inclusive, but it cannot cross this branch cut and go to alpha plus 3 pi, for instance. This branch cut restricts our function and makes it only single valued. But I didn't need to have a branch cut here specifically. I could have it here or here. The point is that all of these branch cuts share the origin in common, and this common point is called the branch point. It's the point shared by all the branch cuts. Let's now describe a special branch cut for the natural log. If we let alpha, our starting angle or starting argument, equal negative pi, then the branch of our natural log that we've extracted is called the principal branch. The principal branch is the branch of the natural log that corresponds to an alpha of negative pi. Now there's a very important note in this branch cut business. The branch that we end up with after the branch cut is not defined on the branch cut. Values of z with an argument of alpha cannot be used in our natural log function. Notice how the theta lies between alpha and alpha plus 2 pi. The rounded brackets mean that the alpha and alpha plus 2 pi are not included in the interval. The function is simply not defined at arc z equals alpha. This becomes important when we're doing integrations involving the natural log, which I'll be doing in the next video. When we're integrating complex functions involving the natural log, we'll be using a branch cut because we don't want the function we're integrating to take on multiple values for the same value of z. When we use the branch cut, we'll have to set up our contour such that it doesn't go through the branch cut, since the natural log isn't defined there. If I make my branch cut down here, for instance, then I have to create a contour that goes around this branch cut, so I can use these two semicircles going around this branch cut, and then integrate along this contour that sort of just avoids the branch cut. I also can't include the origin because the natural log of 0 isn't defined, and because the origin is part of the branch cut, it's the branch point. So that's just a quick teaser of what we'll be doing next. Anyway, that should do it for this video. I'd like to thank the following patrons for supporting me at the $5 level or higher, and if you enjoyed the lesson, feel free to like and subscribe. This is the Faculty of Khan, signing out.